Hello, everyone. So today we're going to be applying a little bit of calculus to our fundamental equations of thermodynamics. So before we get into our equations, let's go ahead and start by reviewing a little bit of calculus principles. So the first thing I want to introduce is the idea of an exact differential. So exact differentials are one of the most important sets of equations that we can make use of. And these are essentially any equation where if I integrate the equation, the answer is simply going to be based on the final state and the initial state of the function. So no matter what path or form the equation has, it's always going to be simply final and initial. Now, these equations are a little bit more infrequent than you'd imagine. But it is worth noting that this is also our definition of a state function. So all of our state functions will form an exact differential. But there is a way to essentially confirm that an equation satisfies, is exact. And that's essentially that it just satisfies what's called the Euler condition. So if I have a function that is dependent upon two variables, if it is a state function, it doesn't matter in which order I take the derivatives. So if I take the derivative of y first and then x, or x and then y, it will be the same either way. However, one of the things you need to do in order to make sure that these derivatives are solvable is when you take the derivative of y, you're going to do so under constant x. Now, it is worth noting that any of our state functions will satisfy the Euler's condition. So that includes internal energy, enthalpy, entropy, Gibbs, and Helmholtz. So let's go ahead and try and apply this to our simplest of the four, internal energy. And last time, with the fundamental equation, we helped show that internal energy was a function of volume and entropy. So if I take the derivative of entropy first under constant volume, followed by volume, that's the same as taking the derivative of volume first under isentropic conditions, followed by entropy. Now, again, this makes a certain degree of sense, but it really has a lot of meaning when I essentially apply these functions to our fundamental equation. Because when I apply this Euler condition, where the first derivative with respect to volume is going to be followed by entropy is the same as entropy followed by volume, then we can remember that the first derivative of internal energy with respect to volume is negative P. And the first derivative with respect to entropy is T. So I can then go ahead and put these two expressions in for my derivatives. And again, we do maintain isentropic and isochoric conditions when we apply these sets of equations. Well, we can then, because these two functions are only a single variable, condense our expression as the negative derivative of pressure with respect to entropy is the same as the positive derivative of temperature with respect to volume. And this is essentially what's called a Maxwell relationship. And it gives us a way to relate the variation of pressure, entropy, temperature, and volume. So this is actually quite a powerful set of equations. And in truth, you can actually apply these to any four of our sets of differential equations. So whether it's internal energy, Helmholtz, enthalpy, or Gibbs. And when we apply these derivatives to each of our four equations, we're going to generate four Maxwell relationships. So when deriving the Maxwell relationships, you can indeed work through them step by step, or you can go ahead and use almost a shortcut version. As we saw for internal energy, what ends up happening is the negative derivative of pressure with respect to entropy is the same thing as the positive derivative of temperature with respect to volume. So, ta-da! But you can also apply this to enthalpy, where you have the derivative of volume with respect to entropy is going to be the same as the derivative of temperature with respect to pressure. So we also find that here. And again, we also see negative derivative of entropy with respect to volume. Again, assuming constant temperature is going to be the same as the negative derivative of pressure with respect to temperature. Two negatives cancel out, and ta-da! And then you can do the same thing with Gibbs. So we generate 4 separate sets of equations. And this gives us a lot of flexibility with how we apply our various relationships of these variables. And it gives us one more very useful tool with determining how we can relate thermodynamic functions. And let's go ahead and work an example of how you can apply Maxwell's relationships. So let's go back a little bit of a ways to, again, our differential equation with respect to internal energy. And now we're going to take the isothermal derivative of our internal energy with respect to volume. Now, when I do this, I have to also apply this derivative with respect to entropy and volume itself, which again just cancels out. And so when I apply these sets of relationships, well, this is when it starts getting a little bit powerful, because it turns out that this is the same thing as our internal pressure. Ooh, that's useful. And it turns out that this is the same thing as temperature, which we got from our fundamental equations. And this is the same thing as negative pressure, which we also got from our fundamental equation. But we can also, using our Maxwell relationships, generate an expression for the ds dv over t, because it turns out this is the same thing as dp dt over v. Well, this ends up giving us another expression to generate a description of our internal pressure for a system as a function of temperature times the change in pressure with respect to T under isochoric conditions minus P. And indeed, we've also already seen a couple of demonstrations of how we can get at this set of variables through use of our expansion coefficients. So this gives us, again, another tool to help condense and play around with our variables, so I don't have to deal with such messy things as change in entropy, and instead get much more measurable quantities such as change in pressure. So again, Maxwell relationships provide another tool to put in our back pocket. So next time, we're going to be spending a little bit more time with the fundamental equation of chemical thermodynamics. Time for a little bit more free energy. Till then, take care.